All right, so let's take a look at something that we're going to call polyprotic acids. And as the name implies, polyprotic means more than one proton. And we might remember that way back in honors chemistry, when we were writing dissociation equations, we would say that hydrochloric acid dissociated into one H+, but something like sulfuric acid dissociated into two H+, and something like phosphoric acid dissociated into three H+. And we kind of left it at that. Unfortunately, that's not quite how it works. They don't just give off 3 protons at a time. And so, in fact, if we were going to use this phosphoric acid as kind of a guinea pig, what ends up happening is when it dissociates, it does so 1 proton at a time. And what you're left with is this version of phosphoric acid, which we're not even going to worry about what the name is. This has a dissociation equilibrium that we're going to call Ka1. The next step would be for this H2PO4 with a charge of -1 to dissociate into its H+ and leave HPO4 2-. And this has its own Ka, Ka2. And finally, this HPO4 2- will dissociate into its own H+ and leave PO4 3-, and we'll call this Ka3. And each of these has a different value, and each of these is a different equilibrium. And there are tables that provide this. So for example, for this particular acid, if I wanted to look up each of these Kas, I would look up for a table, and it comes out looking like this one. And here's our buddy, H3PO4, and it's got 3 values. Ka1 is 7.5 times 10 to the -3rd. It's fairly high, Ka, but still pretty wimpy. It's not a strong acid. Here is Ka2, 6.2 times 10 to the -8, which is 5 orders of magnitude less than Ka1. And finally, Ka3, which is something super dinky, 4.2 times 10 to the -13. This is almost small enough to be negligible. So let's try one of these, and let's take a look at the kind of question that we could expect to run into in a problem like this. Okay, here's the type of question you could expect to run into, and it says calculate the pH and concentration of all species present. When they say species, what they mean is what is in solution when we get to equilibrium. We know there's going to be some H+, and because this is a polyprotic acid and it dissociates in stages, we know there's going to be some H2PO4 -1. We know there's going to be some HPO4 2-, and we know there's going to be some PO4 3-. And we're not going to worry about OH-, although we could find it if we wanted to. And of course, if we know H+, we can also find pH. So how are we going to do this? We're going to treat this like 3 individual acids, and we'll say the first one that we're going to do is the Ka1. So in Ka1, H3PO4 is dissociating into H+ and H2PO4-. That means that the Ka, which for this, Ka1, we said, according to this, is 7.5 times 10 to the -3rd. That's right here. And the expression is going to look like this, H+ and H2PO4-, And on the bottom is our H3PO4, which we know, according to the problem we're starting with, is 0.5 molar. So the first thing that we're going to do is we're going to approximate. We're just going to assume that we can approximate, and if we do that, then what we have is this. So, of course, X is going to be the H plus and the H2PO4, and on the bottom will be our H3PO4, which is 0.5 molar. Now, when you do this, and you solve for X, you get X equals 0.06 molar. And you could easily plug that into H plus and also find pH and also H2PO4 minus. They're the same thing. Problem is that if you do this, this is 0.06 molar over 0.5, and this comes out to be 12% dissociated, which means we can't approximate. So what we have now is doing it by solving for X, not approximating. 7.5 times 10 to the minus 3 equals X. Those are the H plus and the H2PO4. And on the bottom, we're going to have 0.5 molar minus X. So if I crank this whole thing out to solve for X, what I get looks like this. 0.00375 minus 7.5 times 10 to the minus third X equals X squared. And if we get this into the formula for the quadratic by subtracting X squared from both sides, we can solve for X using our quadratic equation on our calculator. You all did that, right? So through the magic of technology, I will solve using my quadratic equation. Now, if you use the quadratic function in your calculator, you'll get two answers. You should get negative 0.065, and that can't be because you can't have a negative increase or decrease in concentration. And you also get 0.057. This lines up better with what we got with approximation. So I'm going to take this 0.057, and this is equal to H plus, which is also equal to H2PO4 minus. So you just got two of those species mentioned in the problem. So I'm going to put that up here. What's our concentration of H plus? 0.057 molar. And if I plug that into my equation to calculate pH, where we take negative log of our H plus, we get a pH of 1.244. Not bad. We also know that H2PO4 minus, because those are the same thing. We get them from the same dissociation equation. And that means that now we have the setup for the next Ka. We'll call that Ka2. And Ka2 has a value of 6.2 times 10 to the negative 8. So let's go down here. We'll say Ka2, which we said was 6.2 times 10 to the negative 8. And here's what's going on in Ka2. H2PO4 minus is going to dissociate and give us H plus and HPO4 2 minus. And of course, these two are going to be equal. Now, we're not going to have to worry about not being able to approximate because this Ka is really small. So here's what this expression looks like. These are both going to be X, and that's going to be H plus, and this is going to be HPO4 2 minus, and this will be our H2PO4 minus that we got from the previous problem. So when we plug all this stuff in, these are both going to be X, and this is the answer from the previous Ka1. So through the magic of technology, I will instantly get my answer. When I do this, I get a value of X that is 5.95 times 10 to the negative 5th. And remember, this is H plus from this dissociation, and it is also the concentration of HPO4 2 minus. Now, we know this. Are we going to add this to 0.057? Take out your calculator and add 5.95 times 10 to the negative fifth to 0.057 and see if you get a difference. And you don't. That means that this value for x is only going to apply to this guy because all the H plus in solution came from the first dissociation. So HPO4 2 minus 5.95 times 10 to the negative fifth molar. All right, last one. This is going to be our Ka3. And for phosphoric acid, Ka3 is something really tiny, 4.2 times 10 to the minus 13th. Let's do it. So in Ka3, what's going on? We said was 4.2? Yeah. We said Ka3 is 4.2 times 10 to the minus 13th. And what's going on in Ka3? HPO4 2 minus is dissociating into H plus and PO4 3 minus. And so this equilibrium expression is going to look like this. H plus and PO4 3 minus on the top. And this is going to be HPO4 2 minus, which was your answer from the previous step. So let's plug that in. These are all going to be equal to x on the top. So x, and this is the answer from the previous problem, 5.95 times 10 to the negative fifth. So I'm going to solve for x. Through the magic of technology, I will get my answer instantly. And I get 5 times 10 to the negative ninth. Well, this is equal to H plus, and it's equal to PO4 3 minus. But you already calculated H plus in the first step, and adding that isn't going to change it. So this only applies to our PO4 3 minus, and that will be right here. 5 times 10 to the negative ninth. So calculate the concentration of all species. You got that one, you got that one, you got that one, you got that one, and you also calculated the pH, and you're done. That's all you do. So take this for a spin, please.